Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Luke Handley and Erik Petigura with us today. Hello, Luke. Hello, Erik.
Hello.
Hi, Frank. Thanks for having us.
Sure. Luke, let's start with you. What's your geolocation? Where are you at?
Currently, I'm in Pasadena. So
Okay.
I'm a first-year grad here at Caltech.
Well, very good. Congratulations. And Erik, where are you at?
I am just across town at UCLA. I'm an assistant professor at UCLA in the physics and astronomy department.
And I gather Luke was an undergrad then at UCLA?
He
Yes.
was, yeah.
Okay.
Luke was one of
Okay.
our shining stars in the department.
Okay.
So
All right. Just trying to make
happy
that
to have him.
connection there
Sad to
because
see
they're
him
not
leave.
too far away from each other.
Yeah.
Very good. Very cool. Good, good, good. Well, I hope you both don't get floated away in this atmospheric river of stuff that's coming your way, otherwise known as wind or rain.
You need the rain.
We'll hope not.
Erik, you got some cool stuff over your board there. What is that?
Well, let's see. Yeah, I've got Carl Sagan, the original, and then got a topographic map of the Big Island of Hawaii, which is where this algorithm that we're going to talk about is being deployed.
Oh, very cool.
And this other stuff is just random squiggles that don't mean anything.
We'll take it as that. Very good. Very good. All right. And Luke, in your early tenure here, what do you like to do for research?
Yeah, so I'd say broadly, I'm interested in using spectroscopy to discover the bulk properties and orbital properties of planets to kind of better understand general architectures and planetary formation.
Cool. And Erik?
So I like to study extrasolar planets, small planets, and one thing that's just been an obsession of mine over the last couple of years is like why these planets we call super Earths and sub-Neptunes are so common. They're like the most common type of planet we know about. Most stars have them, and our sun doesn't have them. So understanding why that is.
Yeah, well, good question. Very good. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era. People, go grab a copy for free. Solving
Nice.
Yeah. Solving the traveling telescope problem with mixed integer linear programming. And Erik and Luke, take us away.
Okay.
So I'm going to let Luke do most of the talking, but maybe I can just sort of give a little introduction to this paper. So this whole project sort of arose out of a specific need we had in the Doppler community. So we do searches for extrasolar planets with the Doppler method. And this involves taking observations over regularly sampled intervals. So like if you're looking for a planet with a 1-year orbital period, you might want to get, say 100 observations every 3 nights.
That would be nice.
And actually scheduling this on the telescope is kind of challenging, especially if you have, hundreds of targets, dozens of programs that you're trying to execute this on.
Yeah.
And for the last 30 or so years, all of this scheduling work is basically done by hand. And this is something that takes a considerable amount of effort, human effort. So for our group, we have somebody who spends most of their time, working on scheduling and making sure the Doppler observations get executed appropriately. And so there was a sort of a major impetus to try to automate this. And really the main motivating factor, the main spark for this is an instrument called the Keck Planet Finder, which is achieved first light in Hawaii about a year ago.
Yep.
And we really want to bring the sort of like scheduling and operations of this new instrument up to the modern era, or at least make it more automated, equitable, repeatable, that sort of thing.
Yep.
So you don't see KPF featured very prominently in this paper. And the reason why is that we were working on this automated scheduling code. And this is what Luke led. And in doing so, we realized that there was an aspect of this problem that was sort of general, which is the challenge of figuring out the optimal order of a set of targets throughout the night. And so what we did was we basically split this research activity into 2 fronts. One, which is actually a different paper in AppJ, on the scheduling of Doppler observations.
Mhm.
And then this is on the sort of optimal ordering of targets throughout the night. They don't
Okay.
have to be Doppler targets or anything. They can be, you know, extragalactic fields
Yeah.
or whatever.
Right.
And we wanted to find a way to do this as efficiently as possible and minimize telescope slews. So for a big telescope like Keck, this can be a lot.
Right.
And so this is really where Luke comes in. And Luke did a lot of really creative work thinking about how to do this, solve this hard problem. And I think I'll let Luke
Really
say a
hard.
bit more about that.
Very nice. Good. Okay.
Yeah, so I think one more important thing to mention is just that, you know, we gave this an initial attempt kind of stitching all of these things together into one big paper. And the result was that not only did we struggle to make it concise, but there were also, you know, a lack of variables and things of that nature. So it got a little bit too complex, so we decided to split it up.
Okay.
And I think the result is that now this is a very well-contained problem and solution, and
Yes.
hopefully we can extend this out to a broader audience, you know, far beyond just the Doppler community.
Very cool. Yep. Scheduling's an issue. LSS.
I suppose
Otherwise.
I suppose we should introduce the traveling salesman problem and then
Okay.
kind of say how that relates to the TTP as well, the traveling telescope problem.
Certainly, yeah. So when we gave this a first try, and we kind of decoupled the problem of scheduling targets throughout a semester and then organizing them within a given night, the first thing that we tried was using the traveling salesman problem and a solution to that. So if you're not aware, the traveling salesman problem is essentially a problem where there's a series of nodes, and you want to find a way to traverse through all of these nodes in real space, while, you know, accumulating the least amount of distance. You know, you want to cover the least amount of distance. And so, you know, this idea is not so different from the problem of observing a bunch of stars or other celestial targets with a telescope.
Right.
The problem, though, is that the TSP is not exactly the same as the telescope problem, or what we're going to call the TTP.
Yes.
And there's a few ways that they differ. And so first, you know, we tried using the traveling salesman problem.
Sure.
The result is that we had, you know, pretty poor results in terms of, you know, actually transferring a traveling salesman model into a real schedule that's kind of, you know, adapting to like current conditions and like globally optimizing this problem. You know, they're very similar on paper, but if you think about it, there are a few key differences that can really get you caught up. And so that's why I sought out to kind of develop, you know, a unique solution to the telescope problem, the traveling telescope problem. And so that is how I came to this. And so the way that this is accomplished is using a method called integer linear programming.
Okay.
So this is, you know, a programmatic method that exists throughout many disciplines. In fact, it's kind of inherently interdisciplinary when you're using it. And so the literature is pretty rich throughout, you know, business and whatnot for big scheduling problems like this. And so using ILP, or what we're going to call MILP, which is where you're not just using integer variables, and we'll explain more what variables are in this framework, but also continuous variables. And so MILP can be used to solve problems like this. That's the bottom line. And
This would
it
be a
has been
good
used in other disciplines.
This would be a good point to just give a shout out to our third author, Velibor Misic,
Oh, yeah.
who is in the Anderson School of Business here, and he really helped us get up to speed on this framework, this mathematical framework, which is more commonly used in the business and sort of operations research. So like how, you know, UPS delivers all of its packages, or, you know, the NFL schedules its games. They're very familiar with this.
Okay.
This stuff.
Well, very nice. Well, there's a nice cross interdisciplinary collaboration there. Very nice.
Yeah, absolutely. Not only was it, you know, a great opportunity to collaborate with, you know, someone within a different discipline, but also it just makes the project really fun, you know, really a good time to work on. So
yeah, very nice, very cool. So I expect you'll be on a business paper soon too. Just reciprocate. Okay, MILPs.
Yeah, so I guess kind of wrapping up our introduction to this paper, um, you know, uh, solving the TTP presents like a really great opportunity for astronomers.
Yeah.
There's a rich literature on the TSP, but nothing really specific to this telescope problem. And so to enumerate a couple of the reasons that they're very different,
Okay.
um, one is that targets are often only accessible for a fraction of the night,
Right.
which means that you kind of have to couple in this problem of making sure that targets are observed between certain time windows,
Yes.
which is, not at all included in the TSP.
Yeah.
Another is that, slew time is not necessarily constant. In fact, it's often, very far from constant. And so that's another thing that you have to consider.
Yes.
Maybe we can show that first figure that shows
Yeah,
this.
exactly. So that leads me
Okay.
to figure one.
Let's take a look. Oh, here we go. Okay. Time-dependent slews. Okay.
So here's a figure. The left plot here is depicting the altitude azimuth frame of Keck Observatory as an example.
Okay.
Um, you can see the blue and yellow lines are the motions of two targets throughout the
Okay.
night.
Okay.
And at azimuth 270 degrees, there's a black line which denotes the RAP limit. So in this framework, we're assuming that the telescope can't cross the RAP.
Okay.
And so this presents, additional difficulties
Indeed.
in slewing between targets. And so the right side is kind of an interpolated curve of what the slew time between those two targets would look like throughout the night at Keck.
Oh, wow.
So the gray line there is, the slew time at every given minute. And so
Wow.
obviously it varies quite a bit throughout the night. And
Yeah.
as we'll discuss more, the way that we kind of capture this within the TTP is creating a slew tensor between every two targets
Okay.
that discretizes this slew curve into different bins.
Okay.
And how you do so is really up to you, but we've depicted it here in a fairly simple way where the length of each slot is uniform. And so basically we want to estimate the
Okay.
slew within each bound. But something important to take away from this is that, when you're estimating at one given value within each bound, there's a big chance that you might, overestimate or underestimate the slew. And so, how you define these bounds and, what value of the slew you choose to pick. I mean, all of these are important things to consider and something that we try to explore.
Interesting. Yeah, it's got some nice twists to the poem. Very good.
So should we get into how this is actually implemented? I guess what I would say is that just to preface this, and of course Luke should explain most of this, is we use the framework of mixed integer linear programming to do this, and there's lots of variables that might be a little unusual to the sort of normal AJ reader.
Okay.
Things like these decision variables with 3 indices. These things are very common in the operations literature.
Right.
But we really worked hard to make this as interpretable as possible to an astronomer. So we went into sort of explaining these variables a little bit more detail than they would be in an operations research paper. And then I'd like to give a shout out to, I think, table 2. It's the table like right, or maybe it's the appendix.
Yeah, it's a beautiful table.
Yeah. And so, just did little things to kind of try to synthesize the variables used in this paper. Yeah, there it is. Yep. So anyway, tried to make this as interpretable as possible.
Great. Very nice.
Yeah, that's a great point. We considered the idea of, whether it was worthwhile to go into depth and include all of the algorithmic details within the main body of the text or to postpone it. But I think ultimately we want to, kind of set a precedent for MILP and problems like this in, astronomical literature and try to make it, actually readable and interpretable to anyone.
Good. Oh, at least I think you did a good job.
Okay, that's good.
Thank you.
Interpretable by me, and I'm certainly no expert at this. So, okay.
Okay, great. So, I guess that kind of finishes up the introduction. And so maybe now we can dive kind of into how the TTP works algorithmically.
Okay.
Um, so the initial conditions for the TTP are that you have a set of targets and an observing interval. Um, and these targets, have variable periods within that interval where they can be observed.
Yes.
Um, this can be, defined arbitrarily for any target. So, if you have a target that needs lower air mass or something like that, this is easy to bake into the initial conditions. Um, but you sort of start with, this condition of an interval for each target where it should be observed. And what we want to do is we want to find a path that observes the most of those as possible, where you waste the least amount of time slewing.
Yes.
And so the way that I figured out how to do this, it was inspired by this paper from Sun et al. In 2018. This is an operations paper where they
Yes.
wanted to optimize pickup and delivery,
Yeah.
with delivery trucks for variable time windows.
So basically, like trying to deliver stuff in LA, right? It takes a much longer time to go between houses when
Yes.
it's rush hour and everything
Yes.
grinds to a halt.
Exactly, yeah. And so this is, a problem that has a lot of similarities within operations. And so that, presented a great opportunity to kind of port a lot of things over.
Absolutely. Very cool.
So, in terms of the framework itself, we have a list of targets. The number of targets is said to be n, and we have a list of nodes ranging from 0 to n+1.
Yes.
I'll get more into why 0 and n+1 are these kind of like dummy indices are important.
Okay.
But regardless, this is how we define the set, and then 1 through n are the actual targets.
Okay. Okay.
And so each node has an associated exposure time and an accessibility window. This is what I was hinting at before. You just need to define the time bounds where you're allowed to observe this target.
Yes.
And an important distinction is that these bounds are when a target can finish being observed.
Oh, yes.
So I think now we might take a look at figure 2 quickly.
Figure 2. Let's take a look at figure 2. Ooh, suboptimal and optimal tours. Okay. There we go.
Right. So here is kind of a visualization of how the TTP is important compared to kind of like a local optimization scheduler, like something that you might get with like Astroplan. So
Okay.
if you traverse between a series of targets, here we have 5 targets. Across the top, these are, altitude azimuth plots of where these targets would be at Keck Observatory
Okay.
as they move across the sky during the night. So time is increasing from left to right.
Yes.
And so this first graphic below that suboptimal tour indicates how you might go about observing these targets. If you were using, Astroplan or something simple, we are not globally optimizing. So the sequence of actions that you might take would be to observe target C, move to target A, and then since target B hasn't yet risen, you move over to the next available target, which is D, and then you come back.
Okay.
And so this is all well and good. You're able to complete the observations, but you're actually leaving time on the table because you're not analyzing the problem in a global way.
Yes.
So the next graphic is an optimal tour. This would be something like the TTP, where you're consciously aware of all of the global solutions to this problem. And you can make a decision that seems like it's suboptimal in the moment, but contributes to a greater global optimum. And so, what you might do is after observing target A is you would wait until target B rises, which is not the intuitive choice at the moment. Then move to the final target. And as you can see, that might, as a result, save you a lot of time.
Right, globally. All right.
And I should mention that, this is sort of a schematic figure. It's not really what we're doing, right, in real life. Like
Sure.
you would see this just intuitively, and you wouldn't really need an automated scheduler to schedule 4 targets anyway. But what we're trying to show more just sort of schematically is the difference between greedy optimization, which is basically taking the shortest slew in the moment, versus taking a global view of the night. And now if you're talking about 50 targets or 100 targets, this is much harder to do, in your head every night. This takes a skilled person, several hours to do. And it's not even globally optimal. So this is just sort of an example of local optimization versus global optimization.
And what is this infeasible tour down here?
Yeah, so the infeasible tour, basically what we're trying to show here is that even with a globally optimized tour among the targets,
Okay.
there still remains the possibility that observing every target that you've assigned is infeasible. So infeasible just means that observing every single target is not
Not gonna
possible,
happen.
even with a globally optimum solution.
Right. There's something physical in the way.
And these infeasible solutions are things that we want to identify, but we don't want to break the code. If someone gives us, 101 targets and we can only schedule 100, we want to schedule those 100 and proceed. So we need to have some way of identifying infeasible solutions and then kind of shaving them off.
Yes, there's value in that. Absolutely. Very cool.
Exactly. Yeah. And one final thing that I'll note before we move on is that I've written in the optimal tour above some points, there are symbols that are T with a superscript E or L.
Yes. Yes.
Those are the time windows for each target. And again, as mentioned in the manuscript, these are the latest times that a target can, these are the times that a target can finish being observed. So it's kind of not intuitively what you think of as the time window, which is just the bounds of when the target is up.
Yeah.
These are the bounds at which a target can be fully observed and finish observing at that time.
Okay.
Yeah, it's an important distinction.
Yes, definitely. Okay.
Should we keep going?
Yeah, thanks for raising that. That makes that a little clearer. Good. Yes, onwards.
Yeah, so next I'll introduce the slew tensor. I guess I already kind of hinted at this, but the slew tensor basically just maps every pair of nodes and a corresponding time bound, a time slot. What is the slew between those two nodes at that time? And so this tensor is pre-computed and just holds all of that information.
Okay. Yes.
And then next, without going into too much detail, we initialize all of the decision variables.
Yes.
So quickly, I'll just say that a decision variable is something that you initialize in a linear program, and it doesn't hold a value until you fully build your model and try to optimize it. So basically, we're using these variables to define, actions or results, and we're building this model, and then in the process of solving the model, we assign values to these variables.
Okay.
So throughout all of this, all of the constraints and whatnot, these are uninitialized. They don't hold any value yet, but they represent something important.
Yes.
And I think without getting into all of the the variables over here, I'd say that the variable x is the most important one, and it just means do you slew from target I to target j within some particular time period labeled as m. And so most of these numbers are 0, but the sort of the task of figuring out the optimal schedule is figuring out what small fraction of those x's you set to 1.
Okay.
Exactly. Yeah. And so basically, after solving the model, you can query this value x for values that are 1 and not 0. And if it holds a 1, then you know that the optimal tour has a slew from I to j during time m or not. Yeah. So Yeah,
Yeah,
I
maybe we can
guess.
get to the performance, and I think figure three shows kind of, the algorithm working as intended.
Yeah, and just one thing. So the total objective here is to minimize the slew time. I think that's worth pointing out again.
Hmm.
Equation.
Yes. Yeah. The objective is to
Okay.
maximize the
Gotcha.
number of scheduled exposures,
Uh-huh.
and then penalize long slews. Yeah.
Yes. And there you go. There's your penalty function. Very good. Okay. Performance. How well and how quick does it work?
Right. So to evaluate the performance, basically what we did was um, we simulated a random night with a random duration. So a duration being a quarter night, a half night, or a full night.
Okay. Okay.
Um, we selected N stars, and we used the California Legacy Survey.
Okay.
Basically, we just needed, targets that were more or less uniformly distributed on the sky that is accessible from Keck Observatory.
And
Yes.
this is just a long-term Doppler monitoring program. So stars are
Yes.
basically spread out uniformly in a solid angle on the sky.
Okay. Okay.
Right. Yes. And we required that the targets, of course, were observable for part of this duration.
And we got to put in, a plug for Doppler science, whenever we can. So of course we
Whenever
use
you
this
can.
as
It's
an example.
absolutely great. Okay.
Right.
Very good. Okay.
And then we, without too much detail, we basically tried to design these problems so that they were difficult but feasible, because we wanted to really push the algorithm to see how quickly it could schedule all of these targets.
Agree a second. Okay.
Well, let's be sure to talk about figure three, because I think that shows
Oh, yes.
the algorithm working
Yeah.
as about as visually as possible.
Right. Yeah. So figure three is a comparison of a simple heuristic and a TTP optimized ordering. So
Okay.
the heuristic that we used was basically something that, an astronomer might code up in a few minutes, which is just, order the targets by their set times, try to make sure that none of the targets set before you can observe them,
Right.
and just move locally through that sequence. And then the TTP, of course, is the global optimization of the same problem. So here in figure
Wow.
three, this is a
Okay.
half night simulation
Okay.
where the number of targets is 50. And so along the top row, you can see the azimuth angle
Okay.
of the telescope. You might notice that it's bouncing around kind of substantially.
Mm.
And then in the TTP ordering, which is on the right side, there's very little movement. In fact, probably the lowest movement. So um, the next row is the same thing, but for elevation.
Okay.
In these simulations, we've set that Keck slews at about 1 degree in either direction per second. So it's important to consider both altitude and azimuth slews.
Mm-hmm.
But the bottom row shows sort of like the condensed amount of time that's being spent during exposures, slews, or is left
Oh,
behind.
yes.
And you can see the takeaway is that the heuristic performs fairly well. You're at least able to observe all of the targets, and
Yeah.
you have a bit of time at the end. But if you optimize properly, the
Mm-hmm.
result is that the slew here the slew is reduced to about 17 seconds per slew, which
Nice.
leaves enough time to observe
Okay.
23 additional targets. You could get 73
Nice.
and 50.
Okay. 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 It's not just
Yes,
you flew, you get more targets.
Yeah.
exactly. Yeah.
That's the real value.
Right. I mean that is the value of
The science, what science of it is you get more targets for a given time period.
exactly.
Nice.
Which is exactly, what we were hoping to achieve. And so it's very
Mm-hmm.
promising that this is what we got out of it.
Mm-hmm. Cool.
So
So I
yeah, so
think,
we
oh, go ahead.
so we performed these simulations with a variety of durations, numbers of targets, and the numbers of slots, M, which is basically how tightly we discretize time,
Yes.
trying to see whether that provides a benefit or not. And so the results of this are kind of summarized in figure 4.
Yay. Results. Let's look it up. Okay.
So
Four. There we go.
Right. So the top row here gives you the runtime of the model. And the bottom row gives you the percent improvement. So by percent improvement, what we mean is if you allot yourself a certain amount of time for worst case slew estimates, how
Okay.
much can you improve on that amount of time using the TTP to optimize the ordering of targets?
Right, relative to that worst case. Okay.
Exactly, right. So if you
Okay.
allot yourself 10 minutes for slewing,
Right.
if you reach 80% improvement, then you only spent, 2 minutes slewing, which is
Got it.
pretty much.
Got it.
So
Okay.
yeah, so you can see the values of M are indicated by color.
Here we go.
And so in general, for the quarter night, which is the first column,
Mm-hmm.
you're looking at, almost instantaneous runtime for M equals 1.
Yes.
And you're nearly tapping out the runtime limit if M equals 10. But if you look at the bottom row, which is the percent improvement, you see that all of these values are more or less the same. And so the takeaway here is that by increasing the amount of time slots that you have, what we thought initially was that you would get better slews,
Yeah.
but in reality, you're adding a lot of computational complexity, but not getting much out of it.
Got it. Got it. Got it. Got it. Okay. Mm-hmm.
And there are similar trends for the half night and full night.
Yes.
And an important distinction is that for the half and full night, you're actually not even solving the problem with, M equals 3 or 10 if you have enough targets. And so the takeaway that we got from this was that, using a lot of different time slots doesn't actually get you significantly better slews. What it does is it boosts the runtime. And so for using
Mm-hmm.
M equals 1, the result was that the percent improvement continued to climb, although it ran much faster. And so in general, the M equals 1 cases
Yes.
turns out to be much more useful.
And I would say this is something that's a little surprising for an observer, because when we're at the
Yes.
telescope and say we get into like a wrap limit trouble where we have to go from one target to another target and we have to unwrap the target, that feels really bad. It feels like we could have made a better schedule.
Okay.
And we really sort of dread that occurring. But it turns out that, on average, that doesn't actually occur that much. And if you just take the average slew time between targets, you get a pretty good answer. Being super sort of fastidious about preventing those wrap limits, is not that big of a deal for the whole night.
Okay.
That being said, maybe this would be a good time to just kind of, start looking toward the future. So, what I would say is that this algorithm, works great. It achieves a, globally optimized solution for 100 targets in a reasonable amount of time on a laptop. This could be ported to more powerful computers, and the commercial libraries that we use to solve it are, parallelized and are meant to be put to, heavy duty machinery. And then, one thing that we explored and, put in the appendix was just sort of heuristic solutions to this problem. It's very common in these like traveling salesman type problems that heuristics do really, really well. And we tried a few. None of them were sort of compelling relative to our global solution. But that doesn't mean that one doesn't exist. So, if someone's interested in kind of picking this up and introducing a new heuristic, they can at least look to see what we've done already. But the heuristics generally run much faster. And I'm sure there's one that would produce something that's nearly globally optimal. We just haven't figured it out yet.
Right, the needle in the haystack. Is the code public? If people want to grab it and try one of their heuristics or anything else, is that available?
So we haven't yet turned the TTP code into, an installable package, although we are happy to share the code with anyone that asks. I think this is something that we'd like to do in the future. We just haven't quite had the time to put it together yet. But, I think that this is a really useful framework and something that we want to share with a lot of people. You can see here that, this is a basic framework, but here in Appendix B, we talk about how there are a lot of ways that you can bake different types of targeting requirements and things of that nature into the framework. And so we hope that it also continues to evolve in that way.
Yeah.
Yeah, so the main body of the paper kind of sort of describes the TTP in its most basic formulation. But then there are certain things that we need to implement for the Doppler searches, such as building in like a certain amount of spacing between repeat observations. Sometimes we like to go back to the same target, say,
Sure.
once per hour. And so we had to figure that out, and we put that in the paper.
Okay.
May not be, useful to many other science domains, but we put it in there just to be complete.
Cool. Very good. All right. That will do. And Luke and Erik, I want to thank you so much for walking us through your very lovely AJ article. That's a great topic.
Great.
Thanks
Thank
a
you
bunch.
for having us.
Yeah,
Yeah,
thanks for
and
chatting with us.
I guess we already kind of covered the future a little bit, unless somebody wants to add some more on where this is going. Oh, so you did mention this is actually on a telescope? It's being tested?
Yeah, we're using it to schedule the Doppler observations of the California Planet Search. And so, in fact, this is being used on two instruments, Keck Hi-Res, which is I think 30 years old now, and this legacy Doppler instrument, and then also the Keck Planet Finder as well, which is a year old. So this algorithm is at least being used in two places. And when I've gone around to other institutions and talked about this, I've gotten a lot of interest basically from people who have, full targets. So, if you're like a extragalactic astronomer and you're sitting on, the Mossfire field, the Moss-Def field, like all night, you don't need this. But if you're looking at, 20, 50 targets a night, this could really help out. And so I'd encourage people to check it out. And we do plan on releasing the code as sort of a standalone package at some point.
Nice. Very cool. Awesome. Luke, Erik, thank you so much once again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Thanks for having us.
Yeah, thanks.